Hello and welcome back to Differential Equations, section 5.2 on eigenvalue method, and this is the part 2 where we are going to discuss those complex eigenvalues. We have seen that when you have a system, you will eventually, that's a bad example, right here, let's say. When you have a system and you convert that, eventually you get some kind of a quadratic form, which we know could have two real distinct answers, a repeated real answer, or a complex conjugate pair. So the goal for today is to learn what's happening when these are the complex conjugate answers. Once we have those complex conjugate answers, they will be also used in some form of this answer to give us the answer for the problem. Now, those answers are also very, very important because remember, a lot of your, or not a lot, all of the wave functions are trig functions, which come from complex solutions to the system. So we are going to have to study this if you want to use them in mechanical and electrical systems. Let's say you're a mechanical electrical engineer. So this is technically you adding 2 plus 2 equals 4. I mean, that's the level of it once you get into serious mechanical or EE work. So what happens when you have complex eigenvalues? Again, we're still in 5.2. This is just the second part for it. So we go and we solve that determinant, right? So we have our dx, dt, whatever, is equal to ax, and then we go through the process of eigenvalues, and those eigenvalues turn out to be complex, meaning lambda is equal to a plus minus bi. So if lambdas are a plus minus bi, and you know the complex numbers like 2 plus 3i or 4 minus I or whatever you have there, then we still have our good old equation to solve. And the question is, first, eigenvectors could be problem, but that's going to be a separate issue because we first want to know what the solution should look like. So the eigenvector, right, could be complex, could be real, and we will see that anytime it's complex, we just keep the real part. We throw away the imaginary part. But or maybe, yeah, I should match the notation. I just looked at the book, and they are using a and b for the vector, and they are using p and the q for the complex number for the eigenvalue. I don't want it to be, I was about to use m and n for the vector, and a and b for eigenvalue, but the book is using a and b for eigenvectors, so it's not going to match notation. So I'm just going to use the same stuff they are using. Okay, so we know that the solution is going to be v times e to the lambda t. Now my vector v, right, is going to be some vector of the form a plus b I, and that's a complex vector, right, where you are going to have a column of these a's, let's say, if you have 3 equations, and then plus, let's say, 3 b's. I mean, you have to have the same number. So that's what it would look like, and then you go through the first one, right, through the second one, through the third one, to come up with those three separate solutions at the end. We'll get there. I just wanted to make sure that you understand the notation with these things. So that's the notation, and then that's multiplied by E, and then we have plus PQI, and then times T. So the solution looks pretty much the same as the solution we are used to from before, where you just have the numbers, right, and you just have this solution. But the trick is that when you have a complex solution, we can use that Euler identity to turn the complex solution into the trig solution, and the trig solution, that's better because the trig solution immediately shows you the wave-like properties of the answer. So you are expecting that your mechanical systems with springs and so on, when you are solving problems, all work out with the complex solutions. And so sorry, mechanical engineers, but 100% of your life is right here, right, when you're dealing with springs and rubber bands and stuff like that oscillates. And the same goes for electrical engineering, right? You are going to deal with alternating currents. And if you're dealing with alternating currents, well, yeah, your capacitors, your inductors, and everything else, those RLC circuits will all be behaving as waves, because alternating current switches the polarity 50 times or 60 times a second, depending where you are in the world. So in this case, right, we are going to change our E, right, using the Euler formula, just like we did before, into the cosine, oh, I forgot the E. E to the PT, that was the real part, and then you have your cosine QT plus I sine QT. So that's a direct over here, the Euler formula, direct swap. There was no algebra done or anything like that. It's just equivalency from the formula. And then we are separating now these into right, with the coefficients of a and a b. So the x solution, right, when you distribute the vector and everything, so everything gets multiplied by e to the pt. That's given. And now when you FOIL this mess, right, you just do basic algebra, right, you will get a, which is a vector, cosine qt, minus b, which is a vector, of sine qt, plus I, and again e to the pt. I mean, we could have just did this for the e to the pt, but whatever. B cosine qt plus a sine qt. Now these are all, again, your column vectors, the one that's all right. So now this is the part where you get to separate the two answers. Remember that your big X is x1 plus x2, or your big Y is y1 plus y2, the superposition of answers. Well, that's now done by taking the real part. So this one over here is going to be your x1 solution, and I have to carefully exclude that, right? This is going to be your second solution. So now technically those two solutions that you get to write for x1 and x2, your x1 solution, and I'm writing this in red obviously on purpose, is e to the pt, and now you have that column vector a of whatever amount of values you have, cosine qt minus b, vector b, sine qt, oops, qt, there we go. And you have your x2, which is the imaginary part, which is also e to the pt, and then you have a b cosine qt plus a sine qt. So you will write your solution in this form. And I'm going to put the box around this, right? So you can quickly find where your solutions are. Now, unfortunately, I can't just pick whatever problem from homework and do it because they did not separate complex versus non-complex, and I don't feel like, you know, trying with my luck 5 different problems until I run into a complex one. So I'm just going to do the lazy thing and repeat the problem that is done in the book, because again, it's going to waste an hour trying to find which problem is complex one in the over there. So here we go. We have x1 prime is equal to 4x1 minus 3x2, and the x2 prime is 3x plus 1, 3x1 plus 4x2. So apparently, right, this is a complex problem, and you can't really tell until you do it. So let's figure out. So my form of dx vector over dt is going to be my matrix A, which is 4, negative 3, 3, positive 4 times vector x. So this is my setup. Now, for those of you still struggling with this notation, dx vector times dt is d dt of the vector which is x1 and x2. So the derivative of x1, right, would be x1 prime, and the derivative of x2 is the x2 prime still in the column vector. The same thing with the vector x is x1, x2 when you do this. So there you go. So that's just to help you with the notation so you can understand this. Now, last time we said that you just have your A, right, matrix, which is 4, negative 3, 3, and 4. And then we do the determinant of 4 minus lambda, negative 3, 3, 4 minus lambda. And then we need to equal that to 0, which will give us the characteristic equation for lambda. And we are going to get those eigenvalues when we solve that equation. In this case, those eigenvalues will be complex eigenvalues. So when we multiply on the diagonal, we have 4 minus lambda squared plus 9 equals to 0. So this is 16 minus 8 lambda plus lambda squared plus 9 equal to 0. And when you put everything together, you get lambda squared minus 8 lambda plus 25 equals to 0. Now, we are expecting the complex solution, so how about we just go and do the quadratic formula. Negative b plus minus b squared minus 4ac divided by 2a. So that's 8 plus minus 64 minus 100 is negative 36. And that's where the complex, right, comes in, because you have a negative under the square root. So this is 8 plus minus 6i over 2, which gives us two complex numbers, 4 plus 3i and 4 minus 3i. Now, one advantage of having the complex roots is that you don't have to do 2 separate calculations, right? You just have the complex conjugate eigenvalue, and you're just using p and q, which are in this case 4 and 3, right? So that's little bit of a plus. Also, we already have a solution. We still have to find those eigenvectors, so it's still not, it's not all, fun and games. But there are a little bit less calculations, right? You memorize the solution, you can just, plug the solution in and all of that stuff. So let's go. When lambda is given as 4 plus 3i, we are looking for eigenvector of whatever that vector turns out to be. Can it be turned, it can turn out complex, could turn out real. Now we'll see. So I have, in this case, remember what we have. We have 4 minus lambda. Now I have to put that lambda in parentheses because of the signs. And then I have, again, the same thing. And then times AB, which are either real or complex, to give us 0, 0. So it's the same calculation as before. Now it's just complex numbers all over the place. Now, what is my matrix over here? 4 minus 4 is 0, so I'm getting negative 3i, negative 3, and then I have 3 and negative 3i times AB to give me 0, 0. Now, if I write these, I get negative 3ai minus 3b equal to 0, and 3a minus 3bi equal to 0. So as you can see, this is now a complex system. And I can divide them by 3 just to make, right, those. I can divide the top one by negative 3 just to get rid of as much of this mess as possible. So I get ai plus b equal to 0, and on the bottom I get I minus BI equal to 0. And these were supposed to be the same equation. Well, we can check that. If I multiply bottom by I get AI, right? Because I wanted to match this term. So if I multiply the bottom by I, and then I times I hope you remember this, I squared is negative 1. So this becomes minus b times negative 1, which is plus b. And that's exactly what I have up there. So they are the same equation. And that's exactly what we needed, right? We need the same equation. That was the... Let me just write this. There we go. That was a requirement. So now I can go either top or a bottom equation. Doesn't matter. You can use the bottom equation. Say A equals BI. So let B be 1, in which case A is, if B is 1, then A is I. And that creates my eigenvector I and 1. So now, if my eigenvector V is I and 1, I can write that as a real plus the complex as a vector. And now, now this is where the linear algebra kicks in on how to decompose these things. But my hope is that you see that I and 1 do not belong in the same column. They belong. Oh, actually, wait. If okay, forget about this. Let's rewrite this way: 0 plus I, and then 1 plus 0i. I hope this helps. So you can see 0, 1 plus 1, 0, I. So I hope you see this. And here is your A, and here's your B. Now, if you have a question, now is a good time to ask it, right? Because, later problems, we use the same thing, and then you get into a 3x3 case, which is worse, right? So I hope that this right, complex values didn't trip too much over here. So guys, what do I have? I have my lambda given as 4 plus minus 3i, from where I need to collect that p is 4 and q is 3. And then I have that my vector v is given as 0, 1 plus 1, 0 I, from where I need to collect that vector a is 0, 1 and vector b is 1, 0. This is what I was after. Because when I have these, they go here. P for P, Q for Q, A for A, and B for B. That's it. But to get to that point, right, you have to do some magic, right, with those calculations. So now it's e to the pt. So my solution now is x1 is e to the pt, so 4t, and then you have your a cosine, so 0, 1 cosine qt minus 1, 0 sine 3t. x2 e to the 4t. Now you put b first, so that's 1, 0 cosine 3t plus a is 0, 1 sine 3t. And that would give you the solution of x1 for x1 and for x2. Now we can right, when you ignore all of these values, if you take a look for x1, you have a vector that it's only sine, right? Because 0 would kill the cosine in this one, and 0 would kill sine in the second pass. So technically, your x1 is e to the 4t, and the only things that survive are negative sine 3t on top and a positive cosine 3t on the bottom. So this is all that it survives for x1. Again, the top should have been e to the 4 going through 0, going through cosine, going to this one, going through 1, going through sine. See, this 0 kills the cosine and only 1 times sine, but it's a negative 1 times sine that survives for the top. The same thing would be if you follow the bottom one. E goes through 1, makes the cosine survive, goes through minus 0, kills the sine. So the bottom one only survives, the cosine survives, and it's positive cosine, and the sine dies because of the 0 in front killed it from the eigenvector. So that's your x1. And then your x2 solution is the same thing, e to the 4t, and then cosine survives on top, and sine dies because it's times 0. Now for the bottom, sine survives, right, and the cosine dies. So what is the solution for the problem? It's you can kick e to the 4t outside, and in parentheses you have c1 times negative sine 3t cosine 3t, and then plus c2 cosine 3t sine 3t. So that's your solution. And now people like, but I like my, separate. This is your vector solution. So now we would like our solution separate. Well, yeah, you can get that, right? Your x1 is going to be e to the 4t, and you just go with the top which is negative C1 sine 3t plus C2 cosine 3t, and the x2 solution on the bottom is e to the 4t again, C1 cosine 3t plus C2 sine 3t. Now that's the one that I want to box, because this is the one where you would, if you had your initial conditions, right, you would go in to find C1 and C2, right? These are all partial solutions before, because you don't have the C1, C2 constant or anything like that. This is the end. You should go back in this problem on YouTube, right? You should go back a couple of times to catch all of the trig and stuff that we did. But one point that I'm going to go back to and say it again, we only did one vector calculation. Remember earlier when you had two eigenvalues, you did two vectors, three eigenvalues, three vector calculations. Well, now when you have the lambda equal a complex number, you are only doing one vector calculation, because that one vector calculation is going to, because the lambda is complex, it's going to produce sine and cosine wave solutions. So you are losing an entire eigenvector calculation, but you are gaining this this algebra here. So, you know, there is never a free lunch, okay? No matter what socialists are trying to prove or say, there is never a free lunch, right? If you're not paying for it, it comes out of your taxes, you're paying it again. So there you go. So now, let's go and take a look at another problem. I'm tempted to actually go into homework and just randomly pick an example and just hope that it's complex. Let's do that. I don't know. Let's try 12. I really don't know. So we have x1 prime is equal to x1 minus 5x2, and x2 prime is x1 plus 3x2. All right, so we have our matrix A, which we all know to extract by 1, minus 5, 1, and 3. And let's see if that gives us complex. If not, I'm just going to abandon it and try the other problem. So we have absolute value, which is determinant, of 1 minus lambda, negative 5, 1, 3 minus lambda, and then that needs to be equal to 0. Now we have 1 minus lambda times 3 minus lambda to FOIL plus 5 equal to 0. Remember, you multiply diagonal, then you come around the other way and subtract the other diagonal. So minus negative 5 is plus 5. FOIL everything, we get 1 times 3, so that's 3 minus 4 lambda plus lambda squared plus 5 equal to 0. This is going to give us lambda squared minus 4 lambda plus 8 equal to 0. Looking good, looking promising, because you can't factor this one, right? The factors of 8 are 1 and 8 and 4, 2 and 4. And there is no way to make 4 with these combinations. So we can't factor it over real numbers. That's, integer values. They could be fractions and still real, but we're not going to know that until we hit this with the quadratic formula. So negative 4 squared is 16 minus 4ac. Yes, we are getting a complex here. So we are getting a complex of a negative 16. So this is 4 plus minus 4i over 2. And we are getting our lambdas to be 2 plus minus 2i. Not a big fan that p is the same as q, because you don't see the, too well the differences where they plug in and so on, but such is life, right? All right, cool. Vector. What is our vector? Well, we get to plug in our eigenvalue into 1 minus 2 plus 2i, and then we have our negative 5, and then we have our 1, and then 3 minus 2 plus 2i, and then times ab to give us 0, 0. Simplify, you get negative 1 negative 1 minus 2i minus 5, and then a 1, and then 1 minus 2i. And then we have our a and b, and then we have our 0, 0. And this is going to give us negative 1 minus 2i times a minus 5b equal to 0. Now, if we did all of the calculations correctly, the second equation will give us the same, but it's kind of hard to figure out what to multiply by to get it. But this is what we get on the second one. 1 minus 2i times b equal to 0. And now you can pick any of these equations to work with to come up with what a and b should be. Now, clearly the second equation is easier than the first one because you already have a single value there, and that's what we like. So from the bottom equation, we have that a is equal to negative 1 minus 2i b. And that is going to give us that if we let b equal to 1, then a is going to be negative 1 plus 2i, which creates our vector v to be negative 1 plus 2i and 1. Now I can write that 1 plus 0i, which gives us negative 1, 1 plus 2, 0i. So we already have that p is equal to 2, q is equal to 2. Now we have that a is going to be negative 1, 1, and b is going to be 2, 0. Again, this is what we were after, because now we get to plug that into the solution. Now, the question is, did you remember the solution, right? The what you're plugging in. It's e to the pt. So it's going to be e to the pt, and then you have your vector a, right, which is negative 1, right, as a fraction. Negative 1, 1, there we go, times the cosine of qt, which is 2t, and then you have minus your vector b, which is 2, 0. There we go, 2, 0 on sine 2t. And done. There we go, sine 2t. Awesome. Now we are going to do the separation here. Oh, before I do that, this was x1, sorry. x2 is e to the 2t. I was looking, I was like, what's wrong? I'm missing something. There's a whole second part that I'm missing that has this one. There we go. Now, what is that second part, guys? If we go back, we We already had this one. There we go. So this one, I was missing the whole second piece, right? So this is the second one, and now there we go. Now we go and write the x is equal to c1 x1 plus c2 x2, and then we can combine the like terms. Now these are all vectors still. Now x kick out e to the 2t because both of them have it. And we have what? C1 is going to have this negative 1, 1 cosine 2t minus another C1 2, 0 sine 2t. Now, we are adding the second solution, so plus C2 2, 0 cosine 2t and plus C2 negative 1, 1 sine 2t. Okay, so that's just plugging in everything into x1 and x2 and factoring out e to the 2t in front. Now, we can separate them now and collect terms, or collect terms first and then separate. But the fact is that you guys can factor this, which will combine C1 and C2, and then factor this, and that will combine C1 and C2, and then you just have to split the ones. Or you can go now on top and pick up the top everywhere with all of the terms and pick up the bottom, right? When I say top, I mean, you know what I mean. I go through this, you go through 1 and then go through 2 and then continue going through top ones like this, right? So pick up the tops and write that all as a one equation, as x1, and then pick up the bottoms and go with the second equation. And then simplify and collect terms. So maybe we can do that. Let's do that. Why not? Or collect terms first and then split them, whatever. So x1 is going to be e to the 2t, and now I need to have four things here. So that's going to be negative c1 cosine 2t minus 2c1 sine 2t plus 2c2 cosine 2t minus c2 sine 2t. And then you have your x2 e to the 2t, and now you do the same thing except you go through bottom ones. So that's going to be e to the 2t. So we have c1 times 1, so c1 cosine 2t. Now the c2 dies at a 0. Then, sorry, this one, c1, negative c1 dies at the 0. This one also dies at the 0 on the bottom. And then you have plus c2 sine 2t. So the only thing that it's left for me is to simplify the top equation, and we're done. So x1, oh, sorry, these are not vectors anymore. They're not vectors anymore because now we separated them. So there are no more vectors in. These are all just constants now, single line. So x1 solution, which would be the displacement of the first spring, going left and right. So, and again, you're doing this just to know where the location is of the object that it's oscillating on a spring. For electrical engineers, right? These are your currents. So you want to know what the current is as you flip the switch on for the circuit you built, right? So what is the current? So in mechanical engineering, we have x double prime, right? X double prime, blah, 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 to give you a solution for x, which is the position of the object. For electrical engineering, you have I double prime, and that will give you I, which is the current, right? Which is, and again, everything is rated for current, right? If your leads are not too good to bring the current through those leads, you have fire on your hands. So x1 simplifies into, put my two cosine terms together, and I'll get 2c2 minus c1 times cosine 2t, and put my sines together. That's going to be minus 2c1 plus c2 sine 2t, and that's after algebra. And then x2 solution, e to the 2t, c1 cosine 2t plus c2 sine 2t. And that ends your calculation. Is the problem over? Yes, for us it is. But if there are initial conditions, yeah, go take some derivatives and plug things in. Whew, right? Guys, these are just 2x2 systems. How about 3x3 system? Right? Well, for 3x3 system, your characteristic equation is going to have 3 answers. And those 3 answers could be all 3 distinct real answers, which means you have to do 3 eigenvalues, 3 eigenvectors calculations, which is what we did previous class in the first half of this lecture. Or you're going to have 1 real with the associated eigenvector, and the other 2 are complex, right? So technically, if I come up with a 3rd degree problem, you are going to have a part of that problem to be the entire problem that we did last class with the calculating value and its vector, and then this problem on top of that one to take care of the other 2 solutions. So there are technically 2 problems glued into one. And can we make it worse? Of course. Could be a repeated solution, could be 5 equations where you have a repeated one and a complex one and the unique one. So you can show all of your math skills right across the chapter in a single problem, because you would have to figure out all of them, right? So yes, the problems you have seen me do in class are the cheapest possible problems that you can get. So if you are thinking that this is complicated, you haven't seen complicated, because this is labeled as the cheapest, easiest possible. There is no easier than this. The complicated stuff is obviously when you involve way more things than this. Now, I'm kind of dreading to do another one of these, because we could go into 5.3 and look at some, pretty pictures. But maybe calculating one of the trees would be somewhat beneficial. And I really don't know which one is going to produce what. They just dumped them all on a pile, 17 through 25. And it's technically the statement of the problem is solve the system and good luck. Like that's literally what it says. So what is this, 20? X1 prime is 5x1 plus x2 plus 3x3. X2 prime is x1 plus 7x2 plus x3. x3 prime is 3x1 plus x2 plus 5x3. Now we all remember, let me just check, 5, 1, 3, 5, oh actually I can immediately write my matrix. So 5, 1, 3, then the next one is 1, 7, 1, yep, 1, 7, 1, and the last one is 3, 1, 5, 3, 1, 5. So we all remember the embarrassment from the last class where I couldn't multiply, FOIL, and factor, and all of that stuff. Here we go again. Let's see if I got better at anything. So to find the determinant, we subtract lambdas on the principal diagonal. And then we do the determinant. Now it's plus minus plus, if you remember. So we have 5, 7, 5. We have these guys 1, 3, 1, 1, 3, 1. I think all is good so far. All right, so we remember it's 5 minus lambda, and then kill the row and a column. So now you have 7 minus lambda times 5 minus lambda, and all of that minus 1, right? Because you have to do this for the remainder. Then we have minus 1, and then we have 5 minus lambda minus, so this times negative 3. There we go. And then the last one is plus 3 times, so kill row and a column. You have 1 minus 3 times 7 minus lambda. That's the determinant for this. Please go look up the videos on how to find determinant of the 3 by 3, right? If you did not take Calc 3 and linear algebra, you don't know this. Like, you're definitely not born knowing it. So if you didn't have Calc 3, you didn't have linear algebra, I understand that you don't know how to find this determinant, and you have to go and learn it. The fact that I know it doesn't help you, right? You need to know it. So go and figure it out. So what do we have here? 5 minus lambda, that's 7 times 5 is 35 minus 12 lambda plus lambda squared and minus 1. The next parenthesis over here, when you distribute negative, actually that's a negative, and then the parenthesis is 2 minus lambda, because 5 minus 3. And then we have plus 3 times 1 minus 21 plus 3 lambda. I hope this is all good so far. Now, 5 minus lambda times lambda squared minus 12 lambda plus 34. And then we have minus 2 plus lambda. This over here is negative 20. So we have negative 60 plus 9 lambda. Okay. Now the big FOIL over here. 5 lambda squared minus 60 lambda plus 150, 170 minus lambda cubed plus 12 lambda squared minus 34 lambda, and combining these guys, minus 62 and plus 10 lambda. Minus lambda cubed, so where are my squares? This one and this one. That's plus 17 lambda squared. Okay, let's see the vanilla lambdas. That's the vanilla, that's the vanilla, that's the vanilla. Meaning linear, if you want to translate that. So that's negative 94, negative 84 lambda. And then the constants, 170 minus 62 is 108, equal to 0. I am not wasting my time on factoring this by grouping lambda squared. Yeah. Let's go and say solve negative x cubed plus 17x squared minus 84 x plus 108 equal 0. And I just hope I don't get any. Oh, such a big disappointment. X equals 2. I mean lambda. No complex values. Lambda equals 2. Lambda equals 6. Lambda equals 9. Lame. We did not get any complex. So we get these, and then we already did the problem like this. So I'm just going to say go ahead and finish this off on your own. Get your V1, get your V2, get your V3, and then write your solution at the end as V1 e to the lambda 1 t plus V2 e lambda 2t plus V3 e to the lambda 3 t. These are all vectors, obviously, here. So, yeah, we did not guess a good problem. I was hoping to run into another complex one, but you can watch this. I gave you 2 complex problems, like one that is done in a book, explained again, and one from homework. I was really hoping that I'm going to hit another one with 3, but we have to move on. Otherwise, semester is going to be over in a month. We're not going to have time for chapters 7 and 8. So I have to cut it here. We'll take a 2-minute break or so, 5 minutes, whatever YouTube takes to refresh for my stream. And then when we start again, it's 5.3.